Welcome to the Explainer. Today, we're going to pull back the curtain on this unseen force. It's one of the most important inventions in all of history, and we're going to get into the simple, really elegant physics that literally makes our modern world turn. So what do they have in common? It sounds a bit like a riddle, right? But the answer is that they all rely on the exact same fundamental principle to work. And it's a force that's all around us, but here's the kicker. You can't even see it. Okay, so what is it? Well, they all run on an invisible engine, and that engine is the electric motor. By the end of this explainer, I promise, you're not just going to understand how it works, you're going to start seeing it, well, everywhere.
All right, let's get right into it. We're going to start with the absolute core scientific principle that makes this whole thing possible. This is where the magic happens, where electricity meets magnetism.
So this key idea is called the motor effect, and it's pretty simple, really. When you have a wire with an electric current flowing through it, and you put that wire inside a magnetic field, it feels a force. That's it. It gets pushed or pulled. This simple interaction is the foundation for everything we're about to talk about. And this image here shows it perfectly. You've got your two key ingredients. First, the magnetic field, going from north to south. And second, you've got your conductor, just a wire with an electric current flowing through it. When that current crosses the field, boom, the wire moves. It experiences a force. It's that simple interaction that we're going to build on. Okay, but which way does it move? Up, down, left, right? It might seem kind of random, but it's not. In fact, there's this brilliantly simple tool that lets you predict the exact direction of that force every single time. Yeah, there's a rule for this, and it's kind of like a secret decoder for electromagnetism. It's called Fleming's left-hand rule, and it lets us map out all these invisible forces at play. Seriously, think of it as a cheat sheet for physics, but one you're allowed to use. Okay, get your left hand ready. Seriously, try this out. Your first finger, point that in the direction of the magnetic field. Now, your second finger, that points in the direction of the current, and then, without even trying, your thumb, well, that's going to point you right to the direction of the thrust, or the force. It's pretty cool, and it works every time. Okay, so we've got the basic idea down, the motor effect, and we have the rule to figure out which way things are going to move. So now, let's actually build a motor. Or at least, let's see how it works on the inside. So here's what a simple motor looks like on the inside. It's actually really straightforward. You've got a coil of wire, because more wire means more force, and it's sitting right there in a magnetic field. Then, of course, you connect it to a power source, like a battery. So let's use our left-hand rule here. See how the current goes one way on the left side of the coil and the opposite way on the right? Well, that means the forces are opposite too. So using the rule, you'll see the force on the left side pushes up and the force on the right side pushes down. And what does that give you? Rotation. That push-pull action is the secret sauce that makes the whole thing spin. But there's a problem. A big one. This works great for, half a turn. But what happens when the coil gets to be perfectly vertical? Well, that's where our simple motor hits a major snag. It would just stop. See, right at that vertical point, the brushes that supply the power actually lose contact for a split second. The circuit breaks, and if there's no current, what happens? The force just disappears, vanishes. The motor would just get stuck, maybe wobble back and forth a bit. Not exactly useful, right? So how do you fix this? How do you get it to keep spinning? Well, the solution is this really, really clever little device. It's called a split ring commutator. And all it is really is a copper ring that's been split in two. That's it. And this is where the genius comes in. As the coil's own momentum carries it past that dead spot, the two halves of the ring swap contact with the brushes. And what does that do? It reverses the direction of the current in the coil. So the side that was getting pushed up is now on the other side, and thanks to that reverse current, and now gets pushed down. It's this perfectly timed switch that keeps the forces pushing the coil around and around in the same direction. Absolutely brilliant. And just like that, the motor has continuous, smooth rotation. It's all thanks to that one simple component. It turns what would be a wobbly, useless coil into a powerful, spinning engine. Okay, so that's the basic principle. But how do we take this simple little motor and, make it matter? How do we make it more powerful? Well, it's actually pretty simple. If you want to make a motor faster, you just have to turn up the dial on one of the three main ingredients. You can either increase the current, just pump more electricity through it, or you can use a stronger magnet. And finally, you can increase the number of turns in the coil. More wire means more force. Simple as that.
And this is why it's so important, because this one basic idea scales up or down, from the tiny little vibrations you feel in your phone all the way to the powerful spin of a washing machine. It's all the same principle. The motor effect is running the show behind the scenes in countless things we use every single day.
So really, every electric motor is just a story of electricity and magnetism creating a spinning force. That's the big takeaway. The next time you hear a blender whirring or your phone vibrating, you'll know what's happening. You're hearing that invisible dance between two of nature's fundamental forces. And that leaves us with one final thought to chew on. We've just seen how moving electricity in a magnetic field creates motion. So what do you think happens if you flip that around? What if you use motion to move a wire through a magnetic field? What would you get then? Well, that is a story for another explainer.